What we're going to do now is the Anti-Markovnikov addition of water to an alkyne. And this mechanism is not in your book. I'm going to use the same alkyne that I used to do the Markovnikov addition. So I'm going to use a terminal alkyne so that I have selectivity between a secondary and a primary carbon. If you're using an internal alkyne, you will not see any selectivity. This is done using hydroboration oxidation. The difference here is the type of borane you're using. We're going to use the bulky borane so that we can only add to one of the double bonds, not two of them. So don't use BH3, you'd have a problem with that one. You do want to use the one that has the two cyclohexane rings on them. Since they're very bulky, it will help protect the double bond. And in the second step, we'd add peroxide and hydroxide. And this mechanism works exactly the same as hydroboration oxidation does. It just occurs once. And we're not going to bother to go through the mechanism for this process, but it does result in the formation of an enol that goes anti-Markovnikov. So you produce the OH on the less substituted carbon and the hydrogen on the more substituted carbon. Okay? And like we saw previously with the Markovnikov's enol, it can tautomerize to its more stable keto form. This time, though, it is done in base. So we're going to show the base catalyzed version of this reaction as we go from the enol to the keto form. I'm going to redraw that the enol form. The base that we have in this particular reaction is hydroxide. So if this is going to be favorable acid-base chemistry, I need to produce a base, the conjugate base, that is equal in basic strength or weaker than hydroxide. So you need to think about the pKa's of the different protons that you see here. The protons on the CH3 group are on an alkane carbon, so their pKa's are around 60, 62-ish. Definitely not a good idea, because if you took those protons, you'd make a much stronger base than hydroxide. If you took either of the two hydrogens on the sp2 hybridized carbons of the double bond, you would produce a really strong base as well. Those protons have pKa's around mid-40s, 43 to 45-ish. Again, you'd make a stronger base or a weaker base, and that's not a good idea. If you took the hydrogen attached to the oxygen, you'd make another alkoxide, which has a similar pKa to the hydroxide's conjugate acid. So that one should be in equilibrium, and that's the one we actually want to take. So we're going to take this hydrogen since it's the most acidic, and it would have an equilibrium similar since you'd be making another OH bond. As that occurs, this OH bond breaks, oxygen takes those electrons, and we'll make an enolate. There's also some water that's been made. The neat thing about this particular enolate is that it also has resonance stabilization of its negative charge. So what I'm about to draw here are resonance arrows, not mechanism arrows. But this oxygen can donate some of its electron density to this carbon, and then you can break the pi bond here to show resonance. So that charge can be distributed over onto what's called the alpha carbon, since it's adjacent to the carbonyl carbon. So now we've made this carbonyl group. And they are in resonance. Okay? The one on the left is the predominant resonance structure because the oxygen can handle the negative charge better than the carbon can. Everybody has an octet in both of these structures, so it's about who can handle the negative charge better. So the one here on the left is the predominant resonance structure. I find, though, looking at the one on the right really helps me see how the product forms a little more easily. Now again, the other product from the last slide was water. And water now needs to act as the proton donor to regenerate the base in this reaction. So now I'm going to show mechanism arrows, And you can do this again from either one of these two resonance structures. I like using the one on the right though, because I can show picking up the proton, breaking the OH bond. It's very simple. If you want to use this other one, you would reform carbon-oxygen double bond, and then the electrons of the double bond would come in and pick up the proton. Okay? Either way, in the end, you are going to produce an aldehyde. So this is the anti-Markovnikov addition of water to a triple bond. And you can see all the carbons are still there. It's just that we've now added water anti-Markovnikov, and then we've done a tautomerization to the keto form. So if you want the aldehyde, you want to do anti-Markovnikov. If you want the ketone, you want to do a Markovnikov addition. So use the appropriate conditions depending upon what you need.